And I guess first thing first, I be a little bit went on like Canvas. I guess some of you guys is aware that like I made some kind of I graded some of you guys for the progress report, and yeah, there's some bugs on Canvas that like some of you like realize that this your score is your grade is exceptionally low for some reason. And yeah, I basically it's a Canvas bug. Like it doesn't it can update whatever going on when I'm using this teacher app like on iPad. So and there's lots of other kind of like bugs on Canvas. I don't know why the university would like to use that. Like probably like has some better. I see like there should be like better LMS like but yeah, we are stuck with that. So but anyway, like whenever like you see something is weird like for your grading, like please feel free to contact us. Like most likely it will be some bug like or like some mistakes. Whenever like you have points deducted, like usually we'll put like some reason like or like at least put something like minus something like here and there. If you didn't see anything, you just like get a grade is exceptionally low or like just contact us. So and and also like I have some questions with the homework. I guess uh it's already late, but please if you haven't even get started, like, make sure you get started already. Um this homework is not exact. I mean, I won't say it's very hard, but if you don't understand what's going on, it will take you a little bit time. If you understand what you're doing, it should be actually quite simple. But um and so and I got some questions like for example like regarding the homework like should you use your own. Okay, I guess like some questions say isn't that like the entire homework is completed, because if you look at let's say let me just get to so say um if we look at the repository, I guess if I can just yeah. So I guess like some of you like it looks like okay, isn't that like already done? Like someone's just like take a quick look and for the yeah, isn't that like everything is done already? Like what I'm supposed to do? Please know that this is the expected result only when you computed the function here. The function is not implemented. You need to read into the code. Like here is a you should implement this function here and also implement this function here if you want to get extra credit. And so on and so forth. If you just try to run this code here, you won't get. I mean, you won't have this image display here. If you unless you have implement this function correctly. Um, and uh, and for this second part here, like the for second questions here, for the second question here, you are supposed to find the, I mean, implement a function to compute the homography. I know that like the OpenCV have like some function like find homography and so on. It would be just one line you calling that OpenCV code, but know that like here like uh, the assignment would like you to implement this from scratch. It's not really that scratch, right? But you're supposed to, as we discussed in the second in the last lecture just before the your presentation, you basically need to construct this matrix A somehow, and then you need to I guess I have some of you guys have to be mute. Uh, so and you need to find the smallest eigenvector, or I should say the eigenvector for the smallest eigenvalue for some matrix, and then like the eigenvector will be basically your homography. After you reshape that into like a 3 by 3 matrix. Um, but you have to like implement that like uh not calling that one line of like open series. Otherwise, yeah, I will give you some point, but definitely you won't get all the points. Maybe you get half of the points. Like if you just simply calling the open series function. Um, and that's it. If you have like other questions and many, please feel free to contact me with Discord. Either the TA or I will answer your question basically. Um, so I guess Discord is the easiest because I'm almost always in front of my computer, and usually it's much easier to explain stuff um in detail, like in writing, because if you just say like I have a problem, like it's hard to know what is your problem. You need to be able to express your problem really for someone to help you. So okay, that's about some logistic thing. So let's just get to uh, what we like to talk about today. So I will mostly using slides today, I guess. So this is my new trick here now. So I'm trying to convert my PDF into sorry, like my PowerPoint into a PDF first before like uh, and then now I can just write it directly on using Suno. So I guess it's easier this way without using PowerPoint. So basically what optical flow is it's like kind of like a techy name here. It's like kind of like a jargon in computer vision. Basically, it's just like you have like two images, let's say, and typically it's like kind of like you can consider it as like two frames, uh, two consecutive frames like from a video, and then like so you have like some object like maybe like this one object like move to another location here. So what optical flow try to do is like try to like estimate like what's the changes to kind of like to find all the changes like in the image like from basically from the second image from the original image. So it's just like this observed changes like this from perception point of view, uh yeah, from the optical point of view. So for example, if you have like some what should I say? Yeah, okay, let's get into the detail, or like I give an example, it probably is clear. For example, like this one. So we have one frame, we have another frame, then it's just like if you have two frames there, like you're able to use the optical flow to get like how each of the pixels move from like one frame to another. So typically, like your optical flow have like uh, different kind of like flavor. One sometimes people call it dense. Uh, so the other one is like, okay, sparse. So for the dense ones, like you're trying to basically for every pixel or like every other pixel, like for each of tiny region, you consider like how the that particular region changes, like, or like particular pixel it changes. For the sparse version, I typically, yeah, just the name suggests you don't go through the entire image. Then maybe you just select some good point to check. In that sense, it's very much like similar to tracking. Um, but we'll talk more about tracking like next time. So, but yeah, in the sense you can also really apparently use open kind of like optical flow for tracking as well, or like the core component of tracking can be implemented with optical flow. So as I said, like it's really the apparent motion. So So it looks like how the pixel changes. Um, the change can be actually caused by like change of like some actual actions, but it may not be as well. So, for example, if you change the lighting, or like even you think of like you just look at like for example, like in the image, there's a TV there. Of course, like whatever going on inside a TV, there'll be some changes there. But your TV does not actually itself a move, right? So it's just track the lighting changes, like but not actually you are able to. But of course, like for computer vision, like, it's always the case, right? You cannot really tell it's really um the TV. I mean, anything inside TV, the scene is moving, or like actually the TV is moving, right? Um, so here, like we will assume that we are trying to find the motion like for each of the pixel. So it will be the dense version we're going to talk about here. So this is a illustration, like yeah, just an illustration. So now okay, I better shut down my other computer. There's some echo. Um, okay, so let's say I have like two frames here, right? So you can consider like uh here I'm kind of like the first frame, let's say is like the frame during is captured like at time t minus one. And then I have the next frame like captured like in this next time step like t here. So if I look at these pixels here, let's say I have like start with like the pixel original like this, I'll have a purple dot here, and you have some motion like it moved to here, and then the green dot moved to here, and so on, moved to here, and so on. Um, Now for the consecutive frames, I'm going to build like this kind of like motion field, or like apparent motion field. As I mentioned, like that's the best we can do anyway. So it's like we will have this motion field will be like have the U and V component will be, for example, like for this here, like at this point, the if this is like X and Y here, the U V X Y will be basically this arrow here. So because or like I should say, maybe something like that, U and V. So will be this is a basically just saying just representing the displacement of this dot, like from the first frame to the second frame. And you do it like for the every pixels, right? Um, and there's some assumptions like for us to construct this UV here. So first thing first, like we want to make sure this like we assume that like from this frame to the second frame here, the brightness doesn't change drastically. So if I have dot here, like have some intensity, or like with this color purple, if I move to another location, it's more or less like still the same intensity. So if it's just change the color, of course, like we cannot track it, right? So the second one is a second assumption is that we assume the motion is relatively small. So it's not going to make a huge motion here, just from here, just suddenly jump to here, let's say. And so we will also assume that there's some kind of like spatial coherence. So let's say if you think of like there's a car here, let's say, okay, it's a bad drawing. It's a car here. So if the car move to some other location here, okay, move to where? Let move to here. Uh, so the pixels uh like on the car will be moved in the same manner, right? So all the pixels here will move also with this kind of like along this direction also, right? So And of course, like at the boundary they won't. But like if you think of like uh the entire image is like composed of like several objects, like at least like for within like each of these objects, like the pixels will be like more or less have coherent motion. So okay, this is just basically repeating like what I just mentioned earlier. Now with this assumption now, we can start to compute this optical flow, or like basically is trying to find this U and V for all of the every pixels. Um so okay, it's a little bit ugly, I don't know. So first of all, like if I think of like from, let's say, from the earlier frame is like xy and t minus 1, right? So let's say if I this dot here, like in the next frame it moved to like x plus u and y plus v here. So we expect that this intensity is more or less like the same, right? Because of this brightness constancy condition or assumption. So and since these two are more or less the same, and I can expand this with Taylor series expansion, right? Because we assume that the displacement is more. We have this is more motion assumption. Like we have U and V is more, so we can use Taylor series expansion. Then like uh, this this one will be approximate as just like IXY T minus 1 multiplied by the okay the 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 x derivative of I and multiplied by uxy plus the y derivative of I and then multiplied by vxy, and also like it multiplied by 1, kind of like, because you have to take derivative of okay, what I mean is like partial I partial x delta x plus partial I partial y delta y plus partial I partial t delta t. In this case, delta t is just equal to 1, right? From t minus 1 to t here. So it's just 1. Um so so therefore I have this um and this should be the same. So if I subtract that, this should be approximately equal to 0, right? Subtracting that, I just got this cancelled. So I have like this is approximately equal to 0. Or I can write it more uh, succinctly as this one here. So delta I transpose is just basically uh, Ix, Iy. Yeah. As Iy multiplied by UV here, something like. Um, So when I multiply, then I get this one, right? So yeah, okay, I just repeating this. Yeah, anyway, yeah, actually, this is not needed. This is already here. So by the way, like for this ix, iy, it, uh, to actually implement that, like we can just, if you remember, we can just use this derivative filter, right, to approximate that, right? For example, like if I want to compute ix, for example, I can uh, approximate with the image convolve a filter like that, right, to be filtered with this filter. And if I want to kind of like take the derivative of iy, then I maybe have like actually I don't have a, let's say I call this image one, uh, ix1, let's say the image one, maybe I write like this, image one, then I1x will be like basically I1 convolved with this filter. So what I mean is, um, Now I know now, so I know how to find ix, iy, and so on. And also it. Uh, uh, Now we are trying to solve for this UV wave. We're supposed to solve for UV for all xy here. Let's slow down a bit, like just think a little bit, like uh okay, maybe I ask a very simple question. Just pause, like make sure you guys are following me. I'm like, so let's say if I have okay, let's say I have this image. I have dimension 512 by 512, right? In the next frame also have dimension 512 by 512. Uh, yeah, this is really simple question. Um, what's the dimension of Ix? Oh, okay. So I mean like so let's say if I have just say like this two, of course these two images have to be the same dimension. Let's say the first one is 5 by 512 by 512, and then second one is like 512 by 512. Um, Now a question is like what is the dimension of Ix? You uh uh yes no that the Ix should be also like 512 by 512. So it's just like what we are going to remember going back to what we of course like if you have boundary, like if you consider the boundary, it may shrink a little bit, like or like 511 by 512 or whatever. But if you we ignore the boundary condition, it will be should be like the same dimension. Um and and for this Ix and for this Ix and so for every pixels, like so for this image here, is basically I have image Ix and I have image Iy and It here. So we just want to make sure that like for every pixel on this image, we should satisfy with this basically. So we can think of like Ix and Iy and It, they are all like with the same dimension, like uh like 512 by 512 here. Now for every pixel of that, we should have like so element wise this one times this uxy plus iy times this vxy plus IT should be equal to 0. And so they are not now because I mean for Sarah's question. So they remember like what we have, like we start with this image here. So we may go back to like something, remember like earlier in this course, like we talk about like this derivative, right? So if we maybe I just should like if I have image here, so if I want to compute ix here, as uh, we mentioned a couple slides before that, it's essentially equal to like this one kind of convolve with a filter, let's say 1 minus 1, something like that, right? So and then when you convolve that will be, you will get something like, if you do padding, you will get something like also an image like of like also 512 by 512, but it's a derivative image. So if you remember, okay, well, what do you remember like okay, maybe I should ask this. So just recall, like kind of remind you guys like what we have, like if we have an image and we do a derivative filter here, so it actually will be kind of similar to a high pass filter in the x direction here. So it's going to detect some edges. So what do you expect? Like you will detect the vertical edges or detect the horizontal edges? Let's see how to do a horizontal. Like, yeah, I have some horizontal like that, I guess. Horizontal or vertical. So if you actually, if you have any image, if you remember, this is just a kind of revision of like what we learned before, like in like, yeah, actually like quite a long time ago now. So if your image, if you kind of like convolve with like, let's say this guy here, yeah, do you, are you going to get a vertical or horizontal? Yes, yes, yes. I guess you guys got it. Yeah. So it'll give you some vertical because it's going to detect like high pass in the horizontal direction, and then like, yeah. So it's just like, okay. But so therefore like this is actually give you a, one of them will give you a horizontal kind of like edges, one of them get you vertical edges. And IT will get you the difference like from two consecutive images basically. So anyway, so we want to have like this equation is satisfied for every pixel. But of course, I can, because you see this UXY here, for each of the pixel, I can have like different UXY, right? So of course I can, there's a lots of variables. I have the entire image of variables. And if you count it, say, okay, if there's a 512 by 512 here, I essentially have like 512 by 512 equations here, right? Because I 512 by 512 equations here. But I have like how many variables here? U here is also 512 by 512. Let me just, I have like 512 by 512 here. Where V here is also 512 by 512 here, right? So I actually have like 2 times 512 by 512 unknowns, but only have like 512 by 512 equations. So of course, like this is like uh, not a well-defined problem, right? So therefore, like what we need is like we have more unknown than the equations, but we can use this what do we call that? I already forgot, like how do we call this assumption? Like okay, spatial coherent assumption, right? That's basically assuming that UV are close to one. Basically U, or I should say not UV are close together, but U and V values, they are close. The values are close when they are close to one another. Okay, what should I say? Like I mean, U x y will be close to like U x plus one y. Let's say when I have like x and y are close to one another, or like let's say U x plus delta x, y plus delta y. So when delta x and delta y are small, then like this value will be close to one another. So to take advantage this coherence assumption. So then okay, maybe before doing that, like exactly trying to solve like U and V, just one remark here. Know that like UV basically you you can only find UV uh kind of realistically when you have what should I say, when there's some distinct features like for the point you're tracking, right? So for example, like if you if for example for the points that you are considering is totally smooth, then there's no way you can know that like where is the displacement, right? This is kind of obvious. Um and also like if you have an edges, let's say if you have a line here, it's hard to tell like the actual motion as well. So for example, like if I have like actual object is moving like this direction, let's say, but if I only look at this aperture here, what it looks like is like the motion could be like this way. It could be look like it's moving this way. And this is like kind of like have this so-called like bubble pole illusion. It's like you even though like you have this thing is just rotating, right? But you looks like this thing is moving upward. Um, and this is a oops, I cannot. Yeah, and this is another other illustration of this bubble pole illusion that you if you just like kind of like put the aperture here, like then it looks like it's moving this way. But if you make it so it depends on the aperture, you just see different things basically. Uh, okay, so this is not what I'm going to want to show next. So, okay, so now okay, now let's really try to solve this UMV now. So as mentioned, like, there will be some ambiguity because we have really more unknowns than the equations, right? So, but a simplest way is like if we want to enforce the spatial coherent constraint here, the really simplest solution will be okay. Let's simply assume that like the values will be the same for every block. So basically, remember what we have is we have like each of these is a potential can have like different UV values, right? So we have like for each of the pixel, like if I have this image, like this is like each pixel here. So each of the pixel can have like different U and V value. So here we will just assume that like separate the image into blocks here. Let's say by 5 by 5 blocks. So each of these block, we assume like inside each of the block, the U and V value will be the same. So like, of course, it's a very rough approximation, but it will work. So then in that case, like we will have, instead of like here, originally I have like how many unknowns here? Maybe like again like so just pause a minute. So if I have like this 5 by 5 block here, so if I don't assume that like this each of these have a different UV here, how many unknowns are here? Okay, I know that some of these questions really simple if you are following, but I don't know whether I really can articulate well today. Woke up too early today, and apparently I didn't have enough coffee. Uh, so and so what I mean by unknown is U and V here. Yes. Okay. Maybe I okay. Let me just you wait. Yes. I'm thinking this may be really. Yes. Yeah, I'm sorry. Like this sounds like so silly question. So yeah. So yes. Um, I regret asking that because I guess some of you get more confused because why you're asking such a silly question. So but anyway, yeah, just so yeah. And if now let's say like what we are doing is like if I take this 5 by 5 windows, what we are going to do is just we assume all the UV here will be the same. So therefore, instead of like 50 unknowns here, I will just have like 2 unknowns because all of them have the same U and V. So then for each of the block, then I will have basically like 25 equations here. I only have 2 unknowns, right? So I can put everything together like this, right? So I have like 25 equations. I have only 2 unknown U and V here. So then I can apparently solve this, right? So this is just like we talk about, okay, before you guys' presentations, right? So solving a kind of a set of linear equations, uh, if you remember that, like if this is ax equal to b. Oh, yeah. So this is a little bit more challenging question. Do you still remember what was that? Like what would be like x? If like I call this as a and I call this as b, like this thing as b. So what will be x then? This is something like you will see all the time. Of course, if you have this is a square matrix, then x will be simply equal to like a inverse multiplied by b, right? So, but this happen all the time is that like actually I shouldn't say this is equal. Of course, I cannot make it equal, but I want to make it as close as possible. Um, and anyone remember that this is essentially the same as um. Of course, when we write this, I will say we say we want to find x such that a is equal to b. Of course, we cannot really find that when a is a kind of a tall matrix like this. So we have more equations than unknown in this case, right? So what we really mean like uh kind of more rigorously will be like something like we want to minimize this the error of that, the mean square error for x here. So, and this will give us, do you count? Okay, by the way, this is something is very good to know. I guess this is probably one of the things is like, so good to know. You should know that, like, even though not because of this class, because uh, for many engineering problems, you keep seeing this kind of problem is that you have an over constraint um, linear uh, linear problem that you have more equations than unknown, and typically it's always you want to find x trying to, or like to find the best unknown, best variable such that you will fit into your this one here to minimize the error. And of course, this is also like a regression problem, a linear regression problem, right? So you think of like I am some data here, so maybe I'm trying to have uh, yeah, okay, let's not go into the linear regression problem there. So, but this one, a quick way to remember that is like, okay, if I if this is a square matrix, of course I can just invert that, right? But the problem, this is not a square matrix, I cannot invert that, right? So let's multiply by A transpose here on both sides. So then if I have A transpose here like this, A transpose will be like IXP1, IXP2, and so on, right? So I have this one, okay, this matrix is a 25 by 2, right? This A transpose here is 2 by 25. When I multiply this together, this will be like a square matrix 2 by 2. And when you are over constraining like more equations than unknown, most of the time like this will be a invertible matrix, or like it will be a full rank. So therefore, like this can be invert, yeah. So this can be inverted. So I if so therefore like you okay. So therefore I can multiply A transpose A inverse on both sides, right? And I multiply by A transpose A inverse here also. So then I will have like X will be equal to A transpose A inverse A transpose B. So of course this is like this is not a proof saying that like if you have this, then you will automatically will be a solution of this. But yeah, it's a quick way to remember, like memorize hey, the solution for this thing. Like this is very useful. So okay, anyway, so yeah, this is just repeating what I said here. So then I can compute I can compute A transpose A. But one thing, like you look at that, like what's A transpose A here? That's something that's actually interesting. This guy here, if you can't remember the Harris corner detector, it's actually the same matrix that we play with, like the M there, like in the Harris corner detector. And there's some physical meaning for this one here. If you remember, like maybe you don't remember exactly here, but maybe you remember this picture here. So if you look at this eigenvalues of the A transpose A there, or like this one here, the eigenvalues of this guy. Okay, remember this picture? So when the eigenvalues, like both eigenvalues are big, then it correspond to places that is a corner. If like you have like one eigenvalue is much bigger than the other one, it corresponds to an edges. So if you have like both eigenvalues are small is correspond to flat region. And so this is a kind of like something we see before, right? So it's like, for example, like for this one, this will be one eigenvalue is be like bigger than the other one. So it's actually this is a both eigenvalues will be small and so forth. Um, and that's actually related to like what was, if you link everything together, it kind of makes sense also. Like you have like okay, maybe I just rewrite the solution here. So remember that like I have uh okay, maybe can I yeah, it's okay. Let me just copy the equation here again. So I have this A transpose A, which will be something like that. This is the A transpose B here. So remember, like I have this X here. So yeah, I can think of like, yeah, if I multiply this A transpose A inverse on both sides, and I have, again, I will have like X is equal to A transpose A inverse A transpose B. Now, if you look, at this one here, if I have both eigenvalues here is small for the A transpose A, it means that like this one is actually either way, like if unless you have both eigenvalues are big, if you have like whenever like one of the eigenvalue is small. Okay, by the way, like if the eigenvalue is equal to 0, it means that like this matrix, maybe I call it just simply this matrix M here. So if I have eigenvalue equal to 0, it means that like I have mx is equal to 0 times x, or like I shouldn't use x, maybe I use a other, maybe z here. For some c is like the eigenvector of m here, right? If I have like zeros is eigenvalue of m here. So that, what does that mean? It means that like m will be, okay, m times c is equal to 0, right? And this is equal to 0 only if and only if that m will not be full rank. Okay, I know like I'm talking too many. Okay, but yeah. So therefore, like this, if this is not full rank, so this won't be invertible. So as you can see, like actually this is also, if you look at the equations here, this is also the constraint that like that is an intuitive connection that like whether this will give you a reasonable solution. So if you have like, let me repeat, like, so if I have, remember that like if I have this place here or xy here is correspond to some smooth or edge region, then I will have one of the eigenvalue equal to 0, right? So if one of the eigenvalue is or like close to 0, then I will have the matrix itself like this one will be have a rank like close to 0, therefore it won't be invertible. So therefore like this will give me a very bad kind of like numerical um, issue here if I try to invert that, and therefore it will give you a solution very inaccurate. So anyway, it's just a remark like on some of this thing. So so I yeah, I guess I will skip this. I am kind of like dragging a little bit slow. So maybe I will just spend some time like to talk about another approach. It's like the same formulation here is that we're trying to minimize this equation here, or like this one here. Mm, yeah, this one here. We want to minimize. Remember, we want to minimize this for every U and V, like or like for every pixels, for U and V at every pixels, basically. So, but earlier we say that like we want to have this spatial coherence condition. So therefore, like one way is like we consider each block have the same U and V, right? So it's kind of rigid. So therefore, like one way to kind of like bypass that is like we will just impose some regularization. So this is like something very kind of typical, like in engineering as well. So it's like we want to have some constraint here for U and V, so that like U and V doesn't change too rapidly. So and you can see here where what we did is basically if we try to minimize this whole thing, right? We want to say this is small, right? Supposingly like this one should be equal to 0 for each of the X and Y location here. So and at the same time, we want to make sure that like U and V doesn't change too rapidly. So therefore, like we just say with some overall the kind of derivative of U and V. So and some square of all of them. So therefore, they won't be too big. So does it make sense? Like, and then we will just integrate over all the XY location there. So this is the Horn-Schunk kind of formulation for optical flow. So then of course like what we want is like just minimize this E, right? So with respect to U and V here. So this is kind of tricky um if you haven't never see this before, because if you think of that, uh U and V is really um a function of X and Y here, and you are kind of optimizing over U and V. So it's like you're optimizing a function of a function. Um, so well, this is just repeating what I said here. So let's write like this entire thing as this L here. So note that like this thing here depends on U and V, and this one here I can write it as a UX plus UY, UX squared plus UY squared, right? Here is a VX squared plus VY squared. So UX and VX, UX and UY are basically the partial derivative of U and partial derivative of uh partial derivative of U in the X and Y directions. So then I can think of them as separate variables. So I can write this L as a this entire thing as a variable of U, V, UX, UY, VX, VY here. And basically we're trying to minimize this integral of this L with respect to this UV, UX, UI, VX, VY, and so on. The way to do that is using this calculus of variation. So, or before that, like think of like if I have E is the like let's say if I have like the optimum, the extremum of E lied on this some U V U X U Y V X V Y here. So then if I deviate by a little bit, so let's say I deviate like U by like epsilon U tilde and V by epsilon V tilde and so on and so forth, where epsilon kind of close to 0 here, then the change of that like over epsilon should go to 0, right? Because this is approximately like the derivative, right? This is approximately the actually this is actually equal to the gradient of E dot um, epsilon u tilde v tilde so forth here. So if I have that is optimum here, is the extremum here, the gradient will be equal to 0, right? So therefore, like if I do the product here, it will be equal to 0 as well. So, okay. So to solve this, we need to, okay, actually, I can honestly, in the past, I was just directly using the calculus of variation, like continue to work like that. But I guess it's probably is a good digression to mention. This is actually just a special case of Euler-Lagrange equation. So maybe okay, this is just a participation question. Like, how many of you heard of Euler-Lagrange equation? So it may be in your. It's just a yes or no question. It probably in. Oh, that's good. Yeah, some of you did. No one. This is a yes or no questions. Uh, okay, okay. Actually, quite a lot. I'm kind of curious. Actually, many of you have did that. Like, that's very nice. I don't know. I remember like where did I learn that? I forgot, but I don't think that I learned it in undergrad though. Or like I didn't really exactly had a class. Now I have so many of you say yes. I'm kind of curious now. So another participation. If you say no, then like you just say not applicable is okay. But if you say yes, like where do you learn that? Like I mean, like from what courses like you come across that? Which courses like you come across that like? So it is another participation question. I know some of you say no, but like for you guys, I would say yes. Like, do you remember like which course? I'm just curious because I don't I which class are you? Okay, you did a complex optimization course, physical mathematics. What was PMath? Huh. AP calculus, communication tool, or physical mathematics. Okay. So I think okay, that's good. So I guess at least like this won't be you guys will have some just a kind of so okay, that's fine. So let's see, like let's consider the 1D case. We have like if you look at this, it's like a 2D case, right? You have U and V and like have X and Y direction, right? But to start with simple 1D case, I say I have like a function L depend on other function like U and also is derivative like in the X direction. So U and UX here. So again, we're trying to find the extremum. So we are trying to, okay, again, I take the integral of this entire function L here and find the extremum of E here. So for the extremum there, we will have like, okay, again, if we vary U by a kind of like U tilde epsilon, it should be equal to 0 for all U tilde. Um, actually, I should add I probably should write something like that. But that's okay, I guess. So then now so that means that like I will have e u plus epsilon u tilde will be equal to this guy here, right? And eu is just this guy. So uh, if I subtract these two, take the difference between these two and divided by epsilon, it should be equal to 0. Now I can expand this guy with Taylor series expansion, right? So if I expand this guy, I have L U U X plus epsilon U tilde partial L partial U plus epsilon U tilde X partial L partial U X, right? Yeah, something like that. So then like uh this guy subtract this one, so I got this one cancel, and I take 1 over epsilon, so I got epsilon cancel. I only have like u tilde partial L partial U here, and ux tilde uh, partial L partial ux here. So this guy should be equal to 0. Now then I can do integration by parts. You see like this guy here have ux tilde, right? If you remember like calculus, from calculus integration by part, I can absorb this like do du tilde multiplied by this guy, then I will have the u tilde partial L partial ux, then with some boundary condition minus uh, integral. I mean, this guy will be something like that. Let's see, u tilde partial L partial u partial L partial x partial L partial ux, something like that. This should be equal to 0. And typically, we can assume this one is equal to 0 using some boundary condition. For example, you just assume like this integrate from like minus infinity to infinity, and you just assume that like u tilde will go to 0 as we go to infinity. So therefore, like these terms will be gone. So we will have like this guy is equal to this guy here. So we have like this one here, and we can pull this u tilde out. So we have like this one u tilde multiplied by this one. And know that like u tilde is arbitrary, right? So we can move kind of like u in any direction, any variation of u tilde. So therefore, we will have this guy should be equal to 0. So if we want to this one to be 0, then we better have like this one equal to 0. So therefore, we have this one. And this is like known as the Euler-Lagrange equation. There are many variations for that. For example, like if you go to, if you have more variables, um, or like in our case, in the 2D case, okay, let's just say in the 2D case directly. We have this 2D case, we have both u and v, and have the x and y direction. I'm not going to detail here. So because you can basically do exactly the same thing, you will end up like two equations. So very similar to before, right? So it's just that you have like one equation for u and one equation for v. Also like for the u equation, let's say, you need to consider not just in the x direction, but also the y direction. So therefore, we have two subtract, two negative terms here. And same for like v here. So therefore, we have these equations, the Euler-Lagrange equations. So now go back to our Horn-Schunk problem here. So we want to solve this guy here. Right? We want to solve this one. And we can use the Euler-Lagrange equation we just mentioned, right? So we basically have this one, right? Take the partial derivative of u minus this is equal to 0. This partial derivative of L with respect to V will, and whatever will be equal to 0. And we can compute the partial derivative for each of these guys here. So with respect to u, v, and so on. So with respect to u, let's say with respect to u, I don't know whether I should pause and then let you to work on one or two of this. Let's say you already see the solution, but like maybe you do not have this like photo photographic memory. Probably is okay. I guess most of you don't. Know that this guy, I guess, just remind you this is a uh, Vx squared plus Vy squared here. So this is like this. Okay, what's partial L partial Ux, for example? So this entire thing is a L here. So this is a question. What's partial L partial Ux? Yeah, it is. Yeah, just what's that value? Yeah, yeah. Oh, okay. Where's that guy? I'm sorry. Like this guy is equal to this guy. Don't forget the alpha here. That's still an alpha here. Yes, I guess it's very simple if you look at that. Like, so yeah. So anyway, so and you can take derivative with other guys. Say if you then like partial derivative with u, so this guy doesn't depend on u, is ux and uy and so on. So only this guy have 2 times this guy multiplied by x and so on. So then you have this, then you can substitute into the Euler-Lagrange equation. So you end up something like this. So you have yeah, anyway, like equations like this. So you can then you can compute u and v. So and of course you have this is a this is actually is a u um this supposedly should be uxx plus uyy and so on, right? But we can approximate this like using this is a actually a Laplacian operator on u here. You again you can use a filter to approximate this. So one filter that approximate this is simply as approximate u partial u square partial square u or Laplace. Okay, anyway, as a simply u minus the average of u. So if we do that, or actually the other way around, the average of u multiplied minus u. So if we do that, let me substitute 2 into that, then we'll have like u and v is equal to this guy. Uh, and of course, like this, I can solve this linear equation here. So I have, yeah, I will have u and v like this. So, and we can solve this iteratively. So every time you take a neighborhood of u, let's say you have some start with some u, and then maybe I'm not sure it's good to start with 0. Maybe you start with something random. Then you take the average of the neighborhood. Let's say I consider u at this particular point, like uxy at this point here. Then I take the neighborhood of u here and compute the average. I got this value. And I compute the ix, iy, and so on, and I compute the v average as well. And then we can iterate get the next u at this value, and so on and so forth. Like you can iterate to solve to compute the u and v fields. Um, okay, yeah, I'm not sure this remark. Maybe I will skip that like, because of time anyway. So yeah, I guess I will skip this one also. Maybe just final quickly mention this like Gunnar Farneback method, because this is actually like you can you see this is like quite popular because it's implemented on OpenCV in OpenCV. Um, this method actually like is on the surface is quite weird because it's really have like some very weird assumption. It basically assumes that like if you have an image, if the image can be represented into a quadratic form. So of course this is a quite weird assumption. If you and if image represented in quadratic form would be something like this dark and then not as dark and so something like that, right? So this is a quadratic form if you think of that. Um, um, but locally maybe you can represent like this. Right? So if you just locally think of an image, maybe you can think of that like it's just any part of the image, maybe just some kind of ellipsoid or whatever, then you can represent like this. So let's say you have like two images. One is like this way. Again, you have two images. One is like this, and then I have another image will be like the shifted version of the first image. So then like let's say F2 therefore will be shifted by D here. So it's also represented by some quadratic form. So therefore will be like X minus D and like this one here. And so therefore like in terms of the second image, let's say you have another B here. So another parameter B here is B2 will be equal to B1 minus 2A1D. Or like if let's say if this is A1, this is yeah, okay, let's I guess I or actually maybe I just shouldn't put A1, maybe just 2AD here. So therefore like if I know if I can fit the image one and image two with this quadratic form, then the displacement there will be simply like this, where I have B2, B1. As I mentioned, like this one is a this B2 is equal to B1 minus 2 A1D. So I can just move the terms around, then I have like D is equal to this guy here, right? And for the A here, I can just approximate with like the average of the first image A, first image A, and then like also the second image A. And yeah, and then that's it, basically very simple things. Maybe I okay, maybe a little bit messy here as I maybe I repeat a little bit here. So again, like what's going on is that you have two images. So you kind of assume the image is like take a quadratic form, simple quadratic form like this. So then I fit the first image with this guy here, let's say with this model here, and then I fit the second image with this second model like this one here. So then I get from the first image, I get some A1 and B1, and then I second image, I get some A2 and B2. And then I would just say, average the A here. I assume A will be just A1 plus A2, take the average of them. And then from that, from what we discussed like here, we can simplify the displacement will be equal to uh, A inverse times B2 minus B1. So it's very simple, honestly. Um, and typically we need to apply for windows. So here we didn't really specify the window. We can specify the windows. So if we specify the windows, we will just say the equation will be modified kind of accordingly. Um, and we can do iterative update as well. So for iterative update will be like, okay, if we already approximated an earlier D here, so let's see, we have earlier D here, say D tutor here. So we will have the A now will be updated not by A1 and A2, not by A1x plus A2x, the average of A1x by A2x, but we will by A1x average with A2x plus D tutor x. So this is like the initial approximate. So let's say, and similarly, we will update the B will be like make changes accordingly because of that. We know there's a displacement for D as well, right? So and then we can update for the D here, and then we can iterate back and forth like this. And that's actually like the Horn-Schunk. Oh no, that's the Gunnar Farneback. Um, and of course, well, yeah, I don't know. Actually, already time, so maybe I should really stop here. Maybe like I will repeat a little bit what I talk uh, about optical flow next time. But yeah, I'm more, yeah, anyway, like that's, yeah. So, okay, I'll see you guys like first day then, like, unless you have any questions, like any questions related to materials here or even for the homework. So if not, then I would just say stop the connection and see you guys like on first day then. Uh, Besides the image, like you mean for the first question, like why do you need to resize the image? Let's see. I can't forget. Like, so actually when you I'm not sharing the screen. Let's see. Let me go back to share my screen. Um, so to stitch the image, like so, okay, basically here, like this function that you're trying to implement is like, yeah, it's what it does, like what it's trying to do is like pretty simple. Uh, if you're given two images, like two homography that you want to kind of warp, so you're going to warp the first image with this homography and the second image with this homography, and both images should be warped with the same with the size given fs by fs here. So you don't actually need to um, resize the image if you just simply use the warp function here. This gives you an example like how to use the warp function, right? So if you just use the warp perspective, like image one with this guy here, and then you warp this, yeah, with this one here, it automatically resize already. So the 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 tricky part here is like when you stitch them together, if you just add them together, then maybe I give an example here. So maybe this one, you can see that like I'm stitching this actually it's very hard to see like because it's stitched quite well here. So if you add the two images together, so of course like for the parts that's overlapping, for example, this part here, you will have the intensity is higher, right? So because you have like double the intensity, you add this with this here, then you double the intensity, right? But for the region here, like if I only have this image, the second image have this part, and this image doesn't have anything, then it only have, compared with this part here, it's only have half the intensity. So therefore, if you want to get the effect that this is seamlessly kind of blend together, you need to make sure that like for the parts that is overlapping, you need to scale it down by 1/2. Yeah. So so therefore like uh, I shouldn't say the difficult part, but yeah, the part that is like a bit more challenging is really the, yeah, you need to figure out like how you are able to scale only this portion but not here, something like, yeah. Okay, so uh if there's no other questions, I will stop the connection. I will see you guys first day then.